or off to the side. I can do that. But yeah. If you send me this file, I'll do it or I'll do it after the broadcast. That's no
problem. Events. It says live now in the YouTubery.
Okay, so we're live. There's your face.
Do it live!
I just got the live stream. So
you got the live stream?
Yeah,
I need a person that isn't me to say that it's live.
Chat says they were live.
Oh, they live.
They live.
They live. Okay, that would make more sense.
Imagine Fraser is making some crazy plan work while racing the clock like in a Star Trek episode. That sounds about right.
Yeah,
it's actually
yeah.
it's not Fraser. Chad.
Yeah.
Instead of deflector dishes, it was fonts, and yeah.
Chad is basically Scotty right now.
Can you invert the deflector dish?
Can you get something on the roof?
Yeah. All right.
Okay.
Let's see, does that work? Can a person talk so we can hear them?
Yes. Hello.
Ooh, they are very quiet.
Person.
There we go. That's fine. Thanks, person. Is that good? Do we want? I mean, is this too much Chad?
Oh wait, I gotta zoom.
Do we want less Chad? I mean,
is it enough for Chad?
I can hardly hear anybody here.
I don't see anything.
It's weird how it switches to your own picture now, so it's when you're talking to yourself.
You turn that light on and then turn that light off. Why don't you kill that light?
Oh my.
I don't think it's plugged in.
Yeah, I like that.
If you double click your own picture, it'll show you a live feed of yourself rather than the one going out.
Yeah,
but we can remove this one. Yeah.
I'd rather see who I'm talking to than talking.
Perfect. Yeah.
I have it permanently on grid mode.
A 5-second lag of my own voice.
Yeah, that's too confusing.
Terrible idea, Morgan.
More Chad. People want more Chad.
Oh no.
Yeah, we'll just flip this around.
Not the 2000 election.
Thanks, John. At least somebody does.
While we're just kind of still getting everything ready, I'm going to say hi to some people. I'm going to say hi to Andrew Planet. And Andrew Planet, thank you, by the way. Apollo is Go, Bill K, Billy Gordon, Ilad Avron, Eric Knapp, Frederick Ulfiz, Guido Bibra, John Gallant, John Suffel, Johnny Zed, Kimberly Cartier is here in the show. Larry Beckham, Linda Sadiq, Momo Dario, Nancy Graziano, Nicole Gallucci, also with us in the show, Noel Rippenthal, Ocean McIntyre, Phil Minecraft, Psycho Cat 749, I think that's like my favorite YouTube name, Sylvan Westby, Stan Sissyfoot, Susan Hunter, Susan Murph, Tech Tang, Versung I'm sorry, here we go, Varsung, Anna Sarimbor, Warbash, Yov Landsman, and Eunice Sofri. So hi to all of you.
No, that's not what WSH stands for. Thank you, Tom. No.
Oh.
Pancakes, though.
So thanks to everyone's constant feedback. We appreciate it. This bar here is now small and down at the bottom, and it doesn't obscure and sit in the middle of the screen. So this thing down here, oh, are you going to try and keep up with the lower thirds, you maniac? Oh, you put them up like briefly and then have them disappear like a documentary. And then that way, if you didn't watch it later on, too bad. So anyway, so this bar down here, this is the commenting that's happening through the WSH Crew Slack. And so the way to find that out is to go to the WSH Crew, WSH-crew.net, and there's an instruction on how you can join the Slack and have your comments appear live in our show. Now, there's also the comments that are happening over on the YouTube, and I'm watching that too. So hopefully we'll be able to get more of you to talk here than in the YouTube, which, you can probably understand why we want to do this. So there we go.
One of the cool kids. Peer pressure.
One of the cool kids, yeah. So that's fine. Just put up the lower third at your discretion, Chad, and then turn it off again. And that way it doesn't obscure the screen. I think that's great. All right. You're just watching the thing get made.
Dustin!
Hear them in my ear.
Do you want louder?
Yeah, they're like really quiet.
There. How's that?
Happy now?
Yeah, it's still quiet.
Still pretty quiet.
Yeah.
Yeah.
What's
Okay.
wrong with your headphones?
I don't know. They're garbage.
Wiggle the thing in the.
Anyway.
Okay.
I can still hear them.
All right.
I think.
That's all
Maybe it's just Nicole. She's the only one who's talking. Okay. You're good?
I
Okay.
can talk.
There we go. Oh, yeah, they're
Oh,
louder.
you're fine.
Okay. All right. Shall we ready to turn this into something that's a little more professional?
We'll give it a shot.
Obviously.
No.
All right. Say when.
Okay. All right.
Okay, here we go. Hey everyone, welcome to the Weekly Space Hangout for Friday, September 23rd, 2016. I'm Fraser Cain, publisher of Universe Today, and this week we've got some cool stories. We're going to be talking about a giant radio space blob, or perhaps a giant space blob in the radio. We're going to see the Hubble Ultra Deep Field, also in radio. I wonder who's bringing these stories. We're talking about a new bill to target serial sexual harassers, but harassers, and Tiangong to crash next year. Sad trombone. The final days of Rosetta, a microlensing circumbinary planet detected, and the repeat of Voyager's Impossible Cloud. And honestly, I have no idea what Voyager's Impossible Cloud is, so I look forward to finding out with the rest of you. Joining us this week, regular gang from around the world today. So we've got Dr. Nicole Gallucci. Dr. G.
Dr. G. How I'm known around
Can you
here.
make Nicole happen?
This part I got to.
How can I not happen?
Those are very
All
steampunk.
technical difficulties. All the technical
No,
difficulties.
I'm Holtzman. Holtzman is not steampunk. They're
Okay.
Are you some kind of
I'm Holtzman.
welder? You weld?
Guys, you haven't seen the new Ghostbusters yet. Just do it.
Oh no, I haven't.
Okay, I haven't seen the new Ghostbusters yet.
All right.
But I love that you are cosplaying in the middle of an episode of the Weekly Space Hangout.
I cosplay in my office all the time.
any day's Dragon Con day. All right. We've got let's go with Morgan Renberg. Morgan.
Hey, Fraser. Hey, everyone.
Oh, where did he go?
Very well.
This isn't gonna work very well, is it?
Oh, give me a second.
I lurk in the shadows.
Switch to
Science at night.
You're a grad student, right? That's the lurk in the shadows.
Is
What
it
is-
because we have too many people?
Don't tell anyone.
We've got.
Okay, well, why don't you just switch to that view? We'll Brady Bunch it.
We'll Brady Bunch
You
it.
can tell Fraser has like 9 monitors.
I do. You can absolutely see
He
me.
sees
Like,
all of us at all
yeah,
times.
yeah,
Yeah, I can see your eyes the way they're going.
yeah. Well, not only do I have 4 monitors, and it's not
Okay.
enough
Oh, and
monitors.
it's doing that thing in the background. This is lovely.
What?
It's Inception.
Yeah.
Yeah.
Yeah. It's
What, with the
creepy.
middle part?
Yeah, the middle part.
Don't worry about it. That's
Okay, all
that's
right.
that's fine.
But we
People
still
can
have everybody on here 'cause we have so
people
many
can
people.
gaze into infinity at the same
Oh
time.
my
Just like
gosh.
Yeah. So we got Morgan Renberg. Hey, Morgan.
Howdy.
And we got Kimberly Cartier. Hey, Kimberly.
Hello, Fraser. Hello, viewers.
And we got Dave Dickinson
Hey, I'm in the same place 2 weeks in a row, still in UK.
in the UK. Okay, awesome.
Still outside Manchester.
And we've got a new face there, a special guest, Dr. Frank Timmies from Arizona State University.
Hi, everyone.
Thanks, Frank. Welcome to the Weekly Space Hangout, and you are our special guest this week.
boy.
Who knows? You might turn into a regular down the road. But today we're going to talk to you about getting your education online in astronomy. So, should we switch to him? What do you think?
We can't even. We've got.
Is it all totally broken?
Yeah, it's just.
We will never see Fraser again.
I'll fix it on the fly.
You gotta fix
You
it.
can talk in a little tiny box for a second.
Yeah.
I'm gonna try to fix all this stuff.
Yeah.
It's gone a little bit sideways.
Where is Fraser? Yeah, I'm not even here.
Why are you up there?
I don't
Oh
know.
my god.
This is just the worst.
You are the worst, but
All right.
All right.
Let's move on.
Yeah.
I can just call Ghostbusters in Hamilton for now.
Is there any way to make him full screen?
Who are we talking to right now?
Dr.
Yeah,
Frank.
sorry,
Special
Dr. Frank.
guest.
Our special guest. Can we make our special guest the whole screen?
Yeah, I'll give it a shot right now.
Awesome.
Okay. I removed that.
I'm gonna mute my noisy self now.
Yeah. Hi, everyone. Welcome to the Weekly Space Hangout for... No. We good?
All right, let's go with that.
All right. Frank, welcome to the Weekly Space Hangout.
Okay. Thank you.
So can you give everyone a quick interview of introduction of who you are and what you do?
Okay, my name is Frank Timmies, and I'm a professor at Arizona State University. And I do research generally on stars, in particular things that go boom in the dark night sky, so supernovae. And I also teach, and I specialize in the introductory courses. I have classes that are ASU online. So I've been teaching online for about 6 years now, since about 2009 or so. And I currently teach the largest college credit astronomy course in the world.
That's fantastic.
Yeah,
So, okay, let's break this into two pieces then. So first, let's talk about your work in supernovae, and then we'll get on to the online education part, which are both super interesting to me and the audience. So, Noel Ruppenthal has titled you an astro-explosivologist, which I think is a good term. So let's talk about this. When I love this, it's just turtles all the way down. So let's talk about the sort of the process of what makes a star go boom when it reaches the end of its life. What's going on here?
It depends on what kind of system you want to talk about.
Let's talk about a type. Let's talk about type 2.
Okay, so we'll talk about a type 2.
What's your favorite kind of supernova?
Oh, I'm pretty fond of white dwarf supernovae these days.
All right.
And in particular, I like scenarios where you have triple star systems making two white dwarfs collide together and go boom.
Yep. What? Okay, so let's go into it. So let's talk about this, because you know what, our fans know absolutely how the supernova work. So let's talk about that.
Okay. So white dwarf supernovae are they're really important for things like measuring distances across the universe. You can win a Nobel Prize if you do it right. And so they're also a good polluter of iron in galaxies. They make a lot of iron group elements and stuff. And so we kind of know what they are phenomenologically. We know how to use them as rulers, as yardsticks, but we don't actually know in detail what it is that is actually exploding. And so it's really one of the, it's the mystery in supernovae is what is these things that are exploding. So for many, many years, the standard paradigm, the standard story was that you had one white dwarf, and surrounding that you had sort of either a main sequence star or a red giant star, and it was sort of dumping its hydrogen and helium onto the white dwarf. That hydrogen and helium would burn to carbon, which would make the mass of the white dwarf grow, and eventually it would get to some magical limit called the Chandrasekhar limit, and then other magic would happen, mainly nuclear physics, and the white dwarf would explode, and that would be that. Many problems with that scenario. For one, you never really see the companion around the star that exploded. You would expect, if it's a red giant or a main sequence, you would at least see some hydrogen and helium. You don't see any of that. But nevertheless, it was sort of the standard paradigm for many years. But it's kind of like a clock. It's like a pendulum. It goes back and forth every now and then. So starting about 6-7 years ago, the pendulum started to swing toward having not just one white dwarf, but having two white dwarfs. And there's two scenarios within that. On the one hand, you could take the two white dwarfs and you can merge them together sort of gently or violently. So
right.
Gently. And so basically you're putting two white dwarfs together that would then also exceed this magical limit, the Chandrasekhar limit, and the things would explode. And then about 6-7 years ago, I was in that forefront where instead of taking heavy white dwarfs, what if you just took two normal white dwarfs, which are about 6/10 the mass of the sun, and you smash them together? What do you get? You get a very interesting event that can be a white dwarf supernovae. So then the question was, how do you get two white dwarfs together? You can look in very dense systems like globular clusters. You can look at centers of galaxies. And you just can't get the rate up high enough in those kind of systems to account for all of the white dwarf supernovae.
So you're not sorry. So you're not going to get them from like we get a white dwarf. Like the future of the sun is a white dwarf, and if the sun was in a binary system, then in theory, if we had a binary companion and that was also a white dwarf, or eventually turn into a white dwarf, as a main sequence star turning into a white dwarf, then you'd have two white dwarf stars orbiting each other.
Right, and with nothing else happening, they would merge on some gravitational wave timescale.
Right.
And that takes a long time. Certainly far below the rate that you see. So then the idea came in was, what if you had a triple star system? What if you had your binary white dwarfs, right? So they're in a binary white dwarf, they're doing their thing. And then you have an interloper out here. You have a third star. It could be anything. It could be a main sequence star. It could be a red giant, just about anything. And that presence of the triple then sets off a Newtonian process where you can exchange the eccentricity, so how elliptical the orbit is, versus its inclination angle. And these are called Kozai-Litoff oscillations. And the point is that it's kind of like them firing two machine guns at each other. Bang, 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 bang. The two white dwarfs get 1 million shots to try and collide with one another. And on average, they will do it enough to pretty much account for the entire observed white dwarf supernovae ray. So I've been kind of a big proponent of selling this idea and promoting it, that triple star systems with a binary white dwarf may in fact, they at least make some and perhaps most of the white dwarf supernovae population.
So then if you've got this situation of a white dwarf supernovae, but it's coming from two white dwarfs or whatever coming together, that's more mass than if you had a white dwarf that was just sipping away its material from a binary companion. So does that put the whole idea of being able to use like a type 1a supernova as a yardstick to see distance out into the universe into question? Or is the signature of the white dwarf supernova different enough that they're not going to confuse each other?
Right. Several points there. So the ones that you use for cosmology are generally filtered down. You filter out the oddballs. You filter out the ones that are superluminous. You filter out the ones that are subluminous. And so you pretty much, by filtering the objects you have, come up with a homogeneous class, that then you can go to town and do your cosmology with. So that's not upsetting that apple cart at all. What you're trying to do is cover the entire spectrum of getting the superluminous white dwarf supernovae and the subluminous white dwarf supernovae. And so you're just trying to cover the whole thing. The interesting thing about the collision scenario is you don't need to get anywhere near this magical Chandrasekhar mass where stuff happens. You can take two ordinary garden variety white dwarfs, 0.6 solar mass white dwarfs each, and if you smash them together, the combined mass of 1.2 will explode as a white dwarf supernovae. Basically explode any white dwarf if you put enough energy into it. And so where the energy is coming from here is the kinetic energy. You're transferring the kinetic energy of the impact into releasing the nuclear energy that comes out. Right.
So it's not just the thing collapsing down inward. It's actually all of them smashing into each other as opposed to that sort of slow.
Which makes for some really great visuals, right? Because people love collisions.
Yeah.
Boom while they do it. Well, actually, it's great too.
Well, we'll just fire up Universe Sandbox and see what happens when we throw two white dwarfs into each other.
Scenario. I watched that one last week. That was cool.
Yeah. Okay. Cool. So let's change gears then. And actually talk about sort of the education that you do online, because that's great. So you say you run the largest
college
graduate credit, the most people online?
The largest college credit astronomy course in the world.
So how many people go through this?
So let me backtrack that and I'll get to that. So what is this? So this is called the Global Freshman Academy. And you can go ahead and Google that, check that out. It's also gfa.asu.edu. And it's a program that offers the entire first year of college, so the freshman year of college, online through Arizona State University. And it's on the edX platform. And so students anywhere in the world can enroll in these courses. There's no admission requirements. And after you finish one of the courses, whether it's my Introduction to Solar Systems Astronomy, or it's English 101, or it's mathematics, then people who are verified, ID verified, and this gets to the academic integrity part. We want to make sure the person actually getting credit is the person they say they are. If you pass that with a C or better, then you can pay $600 to get 3 to 4 units of college credit. And so it's really a kind of a game changer. You're lowering the barrier of entry to college to nothing. I mean, you can take the course for free if you want, and you don't have to pay. We hope you do. We hope you get the college credit and you take that toward building your academic profile and getting your BS degree. Hopefully you do it at Arizona State University, but because we're an accredited institution, you don't have to. You could take those college credits anywhere and carry on your degree at another institution. So it's kind of a new transformative business model and sort of these digital immersion courses, because there's no entry requirements. You only pay after the fact. And it's appealing to learners, who don't have that kind of a degree. So the GFA started about 1 year ago now. So we've just passed the 1 year anniversary. The very first course in this whole freshman year online happened to be Introduction to Solar Systems. So my astronomy course was the first one out the gate. So it was the first MOOC to give college credit as well. In that opening class, so I've taught it now 4 times over the past year. Total enrollment has been on the order in round numbers, about 40,000 students taking the class in total. Over the past years. And so that's how many take it. It was quite a production getting it together once we decided we were going to do this. It reminds me of what we were just doing right here on WSH beforehand. So we spent about a month and a half shooting 64 videos, and we really wanted to do something different, right? We didn't want to do the talking head thing. So I invite you to get on. You can take the course for free. Go ahead and get on, check it out.
That's awesome.
See what it's like. But so it was me out and about, right? So I went to Discovery Telescope. I was out at Lowell. I went to Meteor Crater. I was at the library. I mean, it was just me out and about, not in a studio, chattering about various aspects of solar system astronomy. That was kind of cool.
So we've got a couple of questions here just coming in from the YouTubes. And Emma Robinson wants to know, how do you transfer the credits towards a degree? So if, to take the credits to do through edX and then turn that into something, maybe something more local.
Right. So the actual credit giving process takes through Arizona State University, not edX, right? edX is a platform. And it's ASU that's offering the credit. And then you would transfer it to any other college, just like you would as if you took the courses at a junior college or anywhere else. So that process of transferring credit from ASU to another institution is sort of the normal process by which one goes by with that.
Right.
If you have any questions about this stuff, again, get on, Google Global Freshman Academy. There'll be a link there if you have questions about this kind of stuff, particularly transferring credits or payments or all that sort of stuff. Email them. They'll answer.
Yeah. Okay. So, I mean, how is teaching people through the internet, through this technology, different from being able to interact with your students directly in the flesh?
Okay. Okay. So like I said, I've been teaching online for about, strictly online actually, for about the last 7 or 8 years. And the most important part about teaching online is presence, establishing your presence in the course, that it is yours, that you are there, that you will answer questions within an hour. You don't disappear. And it's that contact is what makes it real. And if you look at some of the reviews of my course, that's almost overwhelmingly the thing that people mention is how much presence we have in the course. And I really think that's key. So in that sense, it's really not that much different than an in-person on-ground course. We try and do things outside the digital realm. So for example, we have a couple of analog projects that we do in the course. One of which is we just invite people to go outside and look at the night sky, right? So whether it's the moon or the sun or a transit, an eclipse, whatever, just get out there and do something. And I'm really surprised how much that resonates, just doing an analog project outside of the digital world. We have them do a camera obscura, right? So we have them measure the diameter of the sun by making a pinhole camera. That one goes over really, really well. And so we have various analog projects that we try and get them to do.
How do you make a camera obscura? Maybe people can do that at home.
Well, you'll have to take the course, Fraser. So I mean, people get very inventive with this, but in the essence of the thing, you poke a hole in a piece of cardboard, and you use that as your lens to the camera. Put it at the sun. Don't look at the sun, and you'll form the image of the sun on the sidewalk on another piece of paper, and you measure the distance between that's your focal plane between the paper you punch the hole in and where the image is. And then you measure the size of the sun on your image there. And from that, you can back out the diameter of the sun. How big is the sun?
That's awesome. Okay, so let's see if we got a couple more questions from people from the internet. So Brian Yoko wants to know, do you think about supernova during your long bike rides?
Somebody's been visiting my website.
Yeah. Yeah.
Actually, the honest answer to that is no. When I go on my long distance touring bike rides, I think the most memorable moments are when my head kind of goes into a Zen mode. I'm not really thinking about anything. I'm not thinking about the pain in my legs. I'm not thinking about the scenery. I'm not thinking about supernova. You're just sort of in this Zen state, and it just goes. So,
yeah. That's cool. Let's see. There was another question there. Larry Beckham wants to know about the supernova that got swallowed by its own black hole before it exploded. Is that? I'm not sure the reference. I don't know if you know.
Yeah, sure. These generally go under the name of failed supernovae. And there are a variety of them, types of ways you can make them. One is sort of you go from a massive star to the direct formation of a black hole, just because the central mass is too big. And if that happens, then you really sort of mute the optical fireworks, the displays that you would get from the explosion. So it becomes kind of a fizzle. It's a failed supernovae. And so people look for these. You can also get a failed supernovae after the fact. So you can make a neutron star first, sort of like maybe like a supernova 1987A or something like that. But then there's enough mass that didn't achieve escape velocity. It falls back onto the neutron star, and you can make the black hole that way. So there's various mechanisms here by which you can make the supernovae fail or be a dud or quasi-fail, or there's a whole variety of scenarios for that. So people are looking for these. Nobody's found a definitive case yet, at least in my opinion. But they're looking.
Yeah. So now we're going to switch to the rest of the show, but before we do, cool. If people want to get involved and actually, take your course, learn more, where do they go? What do they do?
Google Global Freshman Academy. Check it out. Sign up for the course. You can also go to edX and punch in my name, punch in Global Freshman, punch in college credit. It will come up. The course is free. You can take it for free if you like. Go ahead and check it out and do that. Once you do that, if you haven't already, there's a whole number of online providers, whether that's edX or Coursera or any of the others that offer a whole slew of astronomy courses. I know that, for example, Brian Schmidt, who happened to get the Nobel Prize for these 1As that we were talking about earlier, these white dwarf supernovae, he has a course online through the Australian National University. And so there's a number of them. You can probably take, I'm going to guess there's on the order of 20 to 30 astronomy courses that you can take online to bring your general knowledge of astronomy up to a certain level. But the GFA course is the only one for college credit. So if you're interested in moving your academic self forward, we're the ones to go to right now. Thanks.
That's fantastic. And what's the best way to sort of follow you? I mean, people have obviously found your information about how you go on bike rides, but where do you typically communicate with the internet?
I'm a troglodyte.
Hey, if you don't, that's a perfectly legitimate and respectable way to interact with the internet, which is to not.
Mainly through my website.
Yeah. Okay.
That's probably the main one I do.
Yeah. Okay. Fantastic. All right. Well, let's move on with the rest of the news. You're going to stick around, so maybe I'll throw a few softball questions your way if we veer into supernova territory or education. Let's move on to Nicole. Let's talk about your giant radio space blob.
I'm so excited because not only does it use the word blob, the type of object this is a Lyman alpha blob with capital B in the blob. So they're serious about using blob as a scientific word, which I thought was hilarious when I was an undergrad because we did that. And yes, so this is a thing. This is Lyman alpha blob 1. Lyman alpha just means that it's got a lot of hydrogen in it, and it's giving off a certain wavelength or frequency of light that indicates that it's got a whole lot of hydrogen in it. So this Lyman alpha blob was characterized by a number of different telescopes. I say radio because, you guys know me and my love of radio. The Atacama Large Millimeter Array looked at this. Hubble Space Telescope looked at this. The Keck Observatory did some spectroscopy of the first of these huge blobs that they weren't sure what powered them, what gave them so much light. And it turns out what's going on is they have several large, or I think a couple of large galaxies inside them. So there's at least 2 galaxies at the heart of this blob of gas with a whole lot of star formation going on. Lots and lots and lots of star formation gives off lots and lots and lots of ultraviolet light, which can power the radiation from this blob. One of the other fun acronyms, so not only is Lyman alpha blob called Lab 1, there's another fun acronym involved in this study, which is called FIRE, the feedback in realistic environments. FIRE is a simulation of galaxy formation that looks at how this blob can be emitting due to the action of these galaxies. So it's a cool study that mixes observations in radio, observations in optical, I think infrared as well, and this theoretical calculation to look at this very complicated process of galaxy formation that is a very hot topic in astronomy. So yay for science blobs.
There's your blob.
There's the picture of these Lab 1, the giant blob. Yes, there you go.
That is very cool. There's something wrong with either my computer or the internet, but for some reason it's dropping a lot of frames. But the audio's coming through, but I think you're starting to look like slideshows. So I apologize in advance. Chad, do you have any opinion at this point?
I'm not sure if it's the software or not.
Yeah.
It's
so
speeding all the CPU. You're not having a problem at all. So it might just be the internet in general.
Bandwidth.
I think it's
you're fine, Fraser. You're all smooth and stuff, so it's not the program.
Oh, so it's the internet. It's my internet.
Possibly.
You blame Canadian internet.
Hey, Nicole, how far away are these blobs?
These blobs, well, the light from these blobs have taken 11.5 billion years to get to us. This is early in the universe's history, fairly early in galaxy formation stages.
Are they big? Are they small?
Big enough. I don't know what the size is across, but they're big enough to fit at least 2 somewhat massive galaxies, which will eventually combine to create an elliptical galaxy inside.
A couple 100,000 light years, let's say.
Yeah.
That's big.
That sounds big.
Let's just be clear.
Sounds about right. Millions and millions of parsecs.
That's great. You're hired, Frank. That's throw a few more zingers at Nicole. That's great. Sorry, we're doing some.
While they're doing things in the back.
While they're doing stuff, let's chat. Okay.
We're trying to do some.
about
Well, you know what?
blobs.
Let's. We got a bunch of stories. So why don't we move on? We'll let Morgan go next and talk about first a new bill to target serial harassers, which of course has been a common conversation that we've had here on the Weekly Space Hangout, and I think this is a sort of a positive step, right?
Yeah, so over the last year or so, I'd say we've covered several times on this show allegations of physical, verbal, and sexual harassment between faculty members and other people in power against their students, their peers, and others. And there's really no part of this phenomenon that isn't incredibly frustrating. But if you had to pick one piece that was maybe the most frustrating of all, it would be the fact that pretty much all of the accused seem to have been accused in prior workplaces. So they went to one university, they worked for a while, they were accused of sexual assault, for example. This was litigated through the university. Some decision was reached. They left that university, went on to another university, and could start over with a blank slate. And obviously, this is frustrating to the targets and to the population at large, because you're getting these people going out there and basically getting to do this over and over again. It's also frustrating because the institutions, each individually, can claim that they've done their due diligence, they've done the right thing, and washed their hands of it. And that may or may not actually be true in every instance, but certainly there's lots of room available for saying, well, we didn't know anything about this, there was no way that we could have known. And so what this bill does, and this bill has just been introduced into the U.S. House by Representative Jackie Speer, a Democrat from California. And Representative Speer has really sort of been a leader when talking about academic harassment in the House of Representatives. And this bill she's introduced will basically put a level of supervision above universities that can tie them all together. Because each university kind of operates as its own island, but there is the water around all of those universities is the money that universities get from the federal government.
Right.
And so while this university might not be able to talk to that university for one legal reason or another, they can talk to the people who give them the money, what we call the federal funding agencies. And what this bill would require is that any person who has a case brought against them and successfully brought to completion, in which they resolve, yes, something inappropriate did occur here, that university then must tell that person's funding agencies the results of that investigation. Additionally, the university every year must reveal to all of its funding agencies any in-progress investigations. Now, that first category of things, they tell them, so-and-so was accused of this. We found out that was true. This action was taken. In that second set, this is done anonymously. They say, we have 15 open cases against faculty members who received funding from NASA. We're continuing to work on those. And that's basically as far as the bill goes. The idea here isn't to prescribe specific punishments or actions that these funding agencies should take, but to make sure that the information is available to the people deciding who to hand this money out to. And then the hope from Representative Speer and others is that those agencies will then do the right thing and not fund investigators who have had valid accusations found against them, and also to look against funding universities that seem to have lots of open cases that never reach all the way to a conclusion. Because it's no good to open up a lot of investigations if you're never actually finding results one way or the other. And so if this bill were to be enacted into law, and that's still quite a ways off, this would provide a trove of new information for funding agencies to try to make sure they're funding people who are both doing good science and being good academic citizens at the same time.
So, I guess this is one of the issues, right, where people try to move to kind of get in front of these waves of, allegations that they're facing, right? And so by being able to kind of track them from place to place, there's going to be a way and to try and kind of connect this story together, so that the person is potentially a serial harasser, and that you can sort of keep these lines of communication open, right?
Right. So in almost every instance, these things are conducted, these investigations are conducted under agreements of confidentiality. And that means that even if a positive finding, a finding of inappropriate behavior is made, there's very little one university can say to another. Maybe they can say, we had an investigation, but we can't tell you the result. That's no good for anybody. Maybe they can't even say they had an investigation. And so then this person resigns their job, says, I hate living in warm weather and I'm going to go live in the cold. and they sign up for another institution. They bring with them their copious amounts of research funding, and they're able to start this process all over again.
Yeah.
This is designed specifically to try to root those people out and at least expose who they are, so that the appropriate action in terms of not supporting them can be taken.
Yeah.
You know, I guess this, like I said, this is a long way away from being law. We need this bill to be introduced into the Senate. It will have to then be passed out of the committees, and both the House and the Senate reach votes on the full House and the full Senate. There'll have to be agreement between the House and the Senate on their versions of the bills. And this then would be signed into law by the president. And I think one thing that we'll hear a lot about going forward with this bill is questions about the Freedom of Information Act. Because federal funding agencies are federal, pretty much all information that they receive is available to the public if you petition for it. And how information about these investigations will be available to the public at large is a really important question, because that could be a valuable tool for private institutions to use this information of their own volition. I have no idea what.
Sorry, my computer decided it was time to defend itself. So
I feel defended.
You're now protected. There's real-time protection going on. Or we're going to turn that off.
Shut down everything.
Oh no, my PC is now at risk. Well, cool. I think, we have sort of watched this whole system, this whole problem unfold in the last couple of years. We've reported on it again and again. And I think for a lot of the people that are involved, I mean, obviously we've got, some of our regular people here have been through this personally, and it's great to be able to see positive action taken. And I think, we'll keep nagging anyone who'll listen to kind of keep pushing this forward, and we'll keep bringing up these stories as they come out. So
this is a good step, even if it doesn't become law, because it gets the conversation happening in Washington, and then in future sessions of Congress we can come to a more substantive bill.
Yeah. All right, Dave Dickinson, let's talk about the end of Rosetta.
Yes, the European Space Agency's Rosetta mission, after 12 amazing years, is coming to an end at the end of this month. On September 30th, engineers are going to command Rosetta to take the final plunge into the comet. It's actually going to be more of a gentle touchdown. The researchers I've talked to don't like to call it an impact, so I always try to steer away from using that word. It's gonna come down on the comet at about 1 meter per second, which is that's about 3.6 kilometers per hour. So that's actually a pretty bad 5K time for people that run. So actually, it's going to be moving pretty slow. I did ask primary investigator Matt Taylor when I interviewed him at ESA if we're going to see any images after it touches down. He said no, they're going to shut the probe down before it's commanded to shut down when it comes down on the comet. What they're going to do, though, is going to be kind of interesting, is the area of the comet on one of the smaller lobes they're going down on. They're going to try to peer into these sinkholes that we see as Rosetta's been orbiting 67P over the last year or so. They're going to try to look in there and try to get some images really close up. So we should see some amazing images right before the touchdown / not impact on the comet, to kind of see. They want to see these little nodules, cometesimal nodules on the side of the sinkholes that you see there. They want to get a really good close-up look at them. And we actually got to look at Philae. Yeah, there's a good, that's the final impact course right there, kind of a diagram of it. We got to look at Philae a few weeks ago, which was kind of really dramatic to see it sitting there in a crevasse in the shadows. And that kind of explains why we never really heard a lot from Philae. It was just kind of in an area where it didn't get a lot of sunlight, unfortunately. But Comet 67P is probably the most studied comet now up close. So it's been very amazing the last 2 years. And Rosetta was an amazing mission. Launched in 2004, flew by Ida and Gaspra, 2 asteroids, flew by Mars and Earth, took about a decade just to get 2014 was the reawakening, which was kind of, is it going to awaken back up or not? So it's really been kind of a dramatic mission. And it's been a mission that's been going on longer than I've been writing. I mean, almost as long as you've been doing Universe Today, not quite, but it's been pretty dramatic.
I mean, what a sort of amazing time. I saw those pictures of Philae, and it's sort of not surprising that we lost contact with it, sort of jammed it into a little crevasse, and just a leg sticking out on the side. It's sort of a
Also,
pretty sort of
it explains some of those photos we had from Philae where you could see part of like the side of the comet and then looking out into the dark, what exactly. But yeah, my internet exploded that day too. It was on a Monday a few weeks ago when that came around.
Yeah, and so, they were expecting to have this really nice landing, and in fact, it sort of jammed itself here. Chad's going to try and bring up the picture, but yeah, it sort of jammed itself into the side of this rock. It's amazing that, I never thought that we would see this.
We would ever see it.
This picture. Yeah, I never. It was kind of like the Beagle 2. Like I never thought we would ever see Beagle 2 again. Like it was gone, but turns out.
Hopefully an astronaut on Mars will walk up and actually see Beagle up close one day. I don't know if we're ever going to put astronauts on 67P.
Yeah. So here's the picture of Philae here. Yep. And you can sort of see it's turned over on its side, and one of its legs is up on one rock here, and it's just kind of jammed its head into the corner of the comet here. It's really sad.
It bounced several times too. There was some very interesting images of it kind of skittering across the surface of 67P that day. Yeah, so that's too bad, and boy, a lot of lessons were learned for the OSIRIS-REx mission at this point. So hopefully we won't have this problem again. So that's it. Yeah, no, as you said, right? We've been doing this for it took close to 10 years to make the journey to actually make its way to the comet, and now it's time to say goodbye to it. Get there. Yeah, so it's been a really long duration, one of the longer duration missions. The only ones I can think of are like the Voyagers or things that have been out there operating. Mars Odyssey's been operating since 2000. There's not many missions that have been going on this long.
Yeah. I don't know. Do you think it makes sense to sort of wrap it up? I mean, is there any more science that they can pull from it, or it's just going to go around and around and around, right?
I think they've got, it's going to be on this. Well, they can't point it. I asked them that too. Is there any possibility? The problem is Rosetta doesn't have a steerable dish, so they have to move the entire spacecraft to kind of aim it at Earth. And once it's sitting on the surface of the comet, it was never meant to land. There'll be no way to really point it. And I thought, maybe we'll get a few brief pings out of it, once it's there. But they said no, they're going to command it to shut down. So
yeah. With things like Cassini and such, when they're done with them, they crash them into something to prevent, any extra life on the spacecraft from infecting the target, right? Or infecting like Europa or infecting Enceladus, things like that.
Cassini's coming to an end too here in another year. So
exactly, right? And so they are going to take it, and they are going to orient it to crash into Saturn so that it doesn't drop any Earth bugs onto Enceladus. But I guess, it's not that much of a risk. I guess if you drop Rosetta and then it infects the comet, and the comet anyway, I don't think
there's any more comet missions in the pipeline too. That's kind of, we've got OSIRIS-REx and Hayabusa 2. Those are all asteroid missions, but I don't think there's any. I haven't heard of any new upcoming comet missions, so we're not going to see another comet for a while.
Yeah. All right. Well, I think, in retrospect, I think the Rosetta mission was probably one of the best jobs of communicating with the public and building this persona with the spacecraft and the Philae lander and really connecting people with what was going on. And I think the team behind it, both in terms of the science and also just the communicating of the science, it was an absolutely fantastic job of it. There was one sort of major gaffe that we don't need to talk about, but apart from that, it was, I think, a really fantastic mission, and we really appreciate the work they did. So see you later, Rosetta. See you, Philae. Let's move on. Do we want to try shutting down the Zoom and then bringing it back?
Oh, hold on. I can't even go to that view because... Do you want to shut down the meeting?
Yeah, well, we close down the meeting, our first view of the meeting, then bring it back.
Yeah, okay.
Do you want to just point it at me?
Yeah, I'll just point at you.
Okay.
Okay, now we're going to shut the meeting off?
All right, you're going to shut the meeting off.
What?
I'll go to that in a second.
Well, no, we'll be back. We're just going to see.
We'll be back.
We're just wondering if we have a really bad, like our internet connection is super bad on this meeting, but as you can see, I'm
It
really,
shouldn't be. You have like the best internet
yeah,
ever.
I have really good
My
internet.
sweet world.
Wait,
Oh,
that
wait,
worked.
what? Making the window smaller fixed it?
Yeah, there you go. All right, we're
Oh,
back.
come on.
Okay.
All right.
Make it bigger and see
Can,
what
before we
Settle down, Chad.
it works.
That's a cool model.
Okay.
all-
yeah, do you guys remember the paper model that
Yep,
they came
I
out
do.
with?
Yeah.
I just found mine in my office.
Let's see
You want to
the.
put it up?
Yeah, I get a.
Anthropomorphizing space probe.
Faces.
I think that was their. People can't see everyone talking, but we'll show Nicole with her spacecraft in a second. I think that was their great discovery, was to anthropomorphize. Like I think the thing that they figured out with Rosetta, the people sort of working on the public relations side of it, was to anthropomorphize it, to make it this journey that the spacecraft was going on. And I think that was absolutely brilliant. And anyone who works on missions like this in the future should sort of take a lesson from that. So I think that was great.
Oh, that goes all the way into it.
There it is.
Yeah.
Yay.
Yeah.
Yeah, I had to look around my office to remember where I put it.
Yeah. Right?
So
And
cute.
then
I think
and-
we made these live on air, I think, when
oh, really?
yeah, during a
fantastic.
learning space hangout or something.
Yeah. All right. Let us move on and talk to Kimberly about microlensing, about circumbinary planets, and detection.
Yes. So I suppose in today's day and age, the detection of a single extrasolar planet is not terribly newsworthy in most cases. There are nearly 3,400 exoplanets known, but I like to keep up to date with all of the firsts that we ever have in exoplanet science. And there aren't very many left, but this system that was just discovered is indeed a first. The system is Ogle 2007 BLG 349, and it is the first circumbinary planet system that has been detected and confirmed solely using microlensing. And that's actually, I'll get into why that's significant in a minute, but just a few numbers here is this system has 2 low mass stars, each of which is less than half the mass of the sun, so very cold red dwarfs. And in an orbital period 7 years away from those 2 stars is a Saturn mass planet. So this planet itself is not terribly notable. It's pretty average, but it was detected using Ogle, which is one of the 2 largest microlensing experiments that we have. And it was later confirmed using other microlensing telescopes, and then followed up with the Hubble Space Telescope, which is how they realized that this system actually has 2 stars and not just 1. Of all the circumbinary planets we know, there's only about 10 of them. They were all discovered with Kepler, and all of the stars with circumbinary planets are actually much larger than this system. So this is the lowest stellar mass circumbinary planet system as well, which is pretty interesting. But this is really exciting because it's the first microlensing circumbinary system. So it's a proof that microlensing can still detect circumbinary planets. And it's also a proof that circumbinary planets can exist in long orbital periods. All of the systems detected by Kepler have very, very short orbital periods. So these planets are so close to their stars, they're actually on the edge of the stability zone. But the planet that was just discovered by Ogle, that's in a much longer orbital period. So it starts to give us an idea of how frequently circumbinary planets can form and what sorts of configurations and orbits they can actually form into.
So sorry, just the circumbinary.
Sure.
That's the stars are together and the planets are going around the 2 stars, or?
Right. So when we say circumbinary, what we mean is that there are 2 stars at the center of the system instead of just 1, and there is at least 1 planet that is going around both stars at the same time.
Right, and that's sort of the way that you could have a Tatooine, as it were, is if you've got those 2 stars act like a single mass down at the center of the solar system, and then you've got the planet orbiting outside of that common center of gravity, and so that's a stable way that you could have a multi-star star system. And I guess the other way that you could have such
The other way would be to have the stars more widely separated,
right,
and have the planet orbiting just around one of those 2 stars, but the other star is still nearby.
So the vast majority of the star systems in the Milky Way appear to be binary multiple systems.
Yeah.
And sort of we have that comment on the one hand, and then on the other hand, we have this other statement that the vast majority of stars probably have planets orbiting around them. So
Sure.
Which of these configurations is the one that we're going to see the most?
What we're actually going to see the most is the configuration where the planet is only around one of the two stars. The caveats to those two statements that most stars are actually two stars and most stars have a planet. The caveats to those are, yes, most stars are actually in multiple star systems, but those stars are generally very widely separated. It's not quite as common to have two stars that are orbiting very close to each other, because when the two stars start approaching really close to each other, it's very easy to make that unstable.
Right.
So the close binary systems where we see these circumbinary planets are not terribly common. And also, when you then take a close stellar binary system and have a disk of planet-forming material swarming around it, the two stars can actually very easily destabilize the disk before the planets can even form.
Right. Okay. That's really
But if
cool.
if you have wide stars that are separated widely enough, they can still interact with each other, but that extra star most likely will not destabilize the planet-forming disk.
Right. So, I mean, when you're studying these kinds of planetary systems, I mean, does the circumbinary situation setup make things easier or harder to be able to study them?
For us, it actually makes it a little bit more difficult, I would say, because you have two stars that are very close together and they're influencing the same object, which can actually make it difficult to try and essentially separate the two and figure out what is the mass of the first star, what is the mass of the second star, how bright, what temperature, because unless you stare at this system with a very high-powered telescope like Hubble, it can actually be very difficult to get separate measurements of each of the two stars.
Right.
And I like to say is that every exoplanet scientist is really a stellar astronomer in disguise, because most everything that we ever will learn about an exoplanet is highly dependent on what we know about their stars.
Right. You're just really looking at the stars, examining the spectra coming from the star and looking what's missing, seeing how it's changing.
Mm-hmm. Or we're seeing the mass of the planet relative to the star, or the size of the planet relative to the star, or the temperature relative to it's all based on what we know about the stars.
Yeah.
And if we can't separate how each star is contributing flux or energy to the planet, then what we know about the planet just becomes so much more difficult.
I like that way of looking at it. All right, let's move on. Nicole, we are definitely going into WSH overtime. So people have been asking for it, and clearly we have to go a little overtime. But we'll go quickly. Nicole, let's talk about the Hubble Ultra Deep Field in radio.
Yes. So the Hubble Ultra Deep Field is a spot on the sky, small spot on the sky, apparently blank small spot on the sky that Hubble stared at for many, many, many hours to look at a whole bunch of galaxies very far away from us. So through cosmic time, going back close to, not quite super close, but going back billions of years close to the beginning of the universe and seeing these different stages of galaxy formation. Again, galaxy formation, kind of a theme for me today. They pointed ALMA, the Atacama Large Millimeter Submillimeter Array in Chile, at this spot to look and see what that could see. And some of the images show in fact, there's a cool image on the press release, which I will quickly put into the YouTube chat since I know some of you are following along there. In purple in these images, you can see the galaxies that are imaged by Hubble. And then the radio is shown in these orange blobs. Some of them look to be where galaxies are, but not necessarily the brightest galaxies there. So what these orange blobs are signifying are reservoirs of molecular gas, specifically carbon monoxide gas, in these galaxies that are very young, just forming earlier in the universe's history. So this is work that has been done with various telescopes, particularly submillimeter telescopes, for a few years now, looking at carbon monoxide as a tracer of this dense molecular gas, which deep, dense pockets of our forming stars back in this early epoch. And so this is a rather large image showing a number of these galaxies. And the reservoirs of gas that they found didn't necessarily match up to which galaxies they thought would have reservoirs of gas, which is kind of an interesting twist to that story.
Right. I mean, to follow up such a groundbreaking image with such another very sensitive instrument is really cool. And it's sort of too bad Hubble didn't have that in the first place. Is there like a problem with the resolution? Like, with Hubble, you just stare at this area and you just get more and more and more photons, and that's the sensitivity of the Hubble Deep Field is just how much time they spent staring at the same area and just collecting more and more photons. But with the way radio telescopes work, they can't kind of do the same thing, right?
It's a little complicated when you have multiple radio telescopes making an interferometer. Yes, the longer you stare at it, you're going to be more sensitive up into a certain point that is defined by your instrument's limitations. Also, the very geometry of the antennas and how they view the source as the Earth rotates gets you better sensitivity as well. So I don't know how long this observing run was for ALMA, but there are different factors that can help with the sensitivity. ALMA is by far the most sensitive telescope at these wavelengths that has been built so far. So that's why I like featuring the fact that it comes up with all these cool images of things that hadn't been seen before.
Yeah. Morgan, let's talk about the Tiangong 1.
Yeah, I'll keep this quick. Last week, I came on and told you that Tiangong 2 went up. This week, I'm here to tell you Tiangong 1's coming down.
Right.
Where, when, how, why? Well, we know the why, but I can't tell you the answers to any of those other things.
Yeah.
The why is because all the space stations that we have up there are all still experiencing Earth's atmosphere. And so that provides drag and slowly sort of slows them down and they fall back towards the Earth. We actually have to pump up the ISS more than once a year in order to keep it at its current location. The Chinese have stopped boosting up Tiangong 1, and so sometime in the second half of next year, it will fall in some direction, and some pieces of it may hit somewhere on planet Earth. That's about all we know right now.
Right.
Because it's called an uncontrolled deorbit as opposed to a controlled deorbit. We just kind of wait for physics to take over and do its thing. It's not nearly as large as the International Space Station, excuse me. So most of Tiangong 1 ought to burn up. And depending on the angle that it takes, it's possible that all of it will burn up. But it's also possible that some sections will not burn up, and they'll strike somewhere on Earth. The good news is 2/3 of the Earth is water, and we only inhabit a small fraction of the land. So next year, this time, I wouldn't be looking up over your shoulder too much. You're not likely to get hit by a falling Chinese space station.
Right. Every time one of these large spacecraft does this uncontrolled reentry, the internet panics, and so I think this is going to be no different, and people will be watching very carefully to see where it actually does land. It's strange that the Chinese didn't put some kind of deorbiting capability on Tiangong 1.
Well, we don't have deorbiting capability on the International Space Station, and that'll make quite the boom.
But to even aim it into the Pacific Ocean,
So right now we don't have that capability on the ISS. Their plan is.
It's weird that the Americans didn't put the ability to.
Well, it costs money, and we figured it'd last forever.
David,
they'll use one of the docked Progress modules. They'll probably use the engines on it for the ISS to deorbit it over the South Pacific. But yeah, the Tiangong 1, I think it's got a 38-degree inclination orbit, so it'll be somewhere 38 degrees south to north that's a pretty big swath of the Earth.
Yeah.
I haven't seen NORAD track this as a re-entry yet, so it's a ways out. Usually they'll start putting it up on Space Track, so I haven't seen it come up as a re-entry yet, a future re-entry.
Yeah, well, we typically will do some kind of, pool where we try to guess when and where it's going to land. You know, we try to add a little levity because I mean, I just guarantee the some websites will start to try to freak people out. So
Oh yeah.
yeah. All right, well, let's move on. Kimberly, last story: the repeat of Voyager's impossible cloud. What?
Yeah. So I guess I should start this story back in 1980 when Voyager 1 actually flew by Saturn and turned its IR probe over to its moon Titan. And while Voyager 1 was looking at Titan in the infrared, it detected a cloud made out of a particular molecule. And I'm hoping I'm not going to butcher this chemical name. It's dicyanoacetylene. Okay. It discovered a cloud made out of dicyanoacetylene. And what made it impossible was that the amount of the gas that Voyager detected was 1% of the amount of gas that should have been there for a cloud of that size. So it was missing 99% of the gas that should have been there for a cloud of dicyanoacetylene that size. They weren't particularly looking for it, but they saw this very strange cloud. Unfortunately, we didn't realize how strange this cloud was right away. By the time we realized it, Voyager 1 was way past Saturn on its way out of the solar system, and we sort of put this impossible cloud on the back burner until just recently when Cassini spotted a similar cloud made out of dicyanoacetylene. And again, there was 99% of the expected gas was missing. So given that these two clouds are 36 years apart, probably not the same cloud. So these two clouds have to form by a process that happens fairly regularly on Titan. They used Cassini's IR spectrometer to figure all of this out. And the prevailing theory is that instead of this particular gas, dicyanoacetylene, going through the normal cloud condensation process to make its way up to Titan's stratosphere where this was detected, instead of that, they think that this particular gas now forms using solid state chemistry, which means that it forms on the surface of a particular particle instead of just condensing from a gas-like state into clouds. What's really exciting about it is that this solid state chemistry that we think is happening to form these clouds actually also happens on Earth, up at the poles. And it's part of why there's ozone depletion up at Earth's north and south poles, is because of this solid state chemistry that produces ozone depleting molecules. But on Titan, you take a solid ice particle of cyanoacetylene and you cover it with hydrogen cyanide, and then you bombard it with UV particles, and then you create a very thin shell of the dicyanoacetylene that was detected. So instead of having a whole cloud full of these particles, solid made out of this material, you just have particles with a very thin shell of it.
So how does that affect my ability to stand on the surface of Titan and take off my helmet?
You probably still don't want to do that.
Okay.
But Titan is the object in the solar system that we keep comparing to Earth because it has the weather patterns, the oceans, the dunes, and everything. And now we're finding even more processes on Titan that we also have analogous processes for on Earth. The connections between the two different environments are becoming, there's just more and more of them.
It's just another instrument to put on our future Titan sailboat.
Yes, definitely.
All right, cool. All right, well, let's start to wrap things up now. But before we do go, I want to thank everyone for sticking with us as we went through some technical issues today. We learned a couple of very valuable life lessons. Like if you have a maximized Zoom meeting and your CPU usage starts to go through the roof, just resize the window and it'll fix it. Also, if a person says my name in Slack, that pauses the Slack chat. Go ahead and do it now. So
everybody's gonna do it.
Yeah, and everyone's gonna do it now. Fraser. So anyway, we will have. See there, you've done it, Nicole. Now it's gonna jam up the Slack. But once again, if you want to join the conversation, the Slack down here, as this gets more and more, and just the great community of the WSH crew. I highly recommend. Do a search for the WSH crew. They are really the producers behind the scenes. They're the ones who helped organize Dr. Frank Timmy's this week and all of our special guests. So we really appreciate them. Let's see everybody there. Big thanks to Chad, who is about to disappear for a couple of months. So yeah. So I might have to rope my son into being my engineer. We'll see what happens, or I might have to do it on my own. So it'll be a less interactive experience. Yeah. So let's move around the list here, and we'll give people a chance to shamelessly self-promote what they're working on and how we can find out more. Dr. Nicole Gallucci, where do we find out more?
Hi, I'm Noisy Astronomer, and right now I am particularly promoting the DIY Science Zone for Geek Girl Con, October 8th and 9th in Seattle. We are raising money so that we can get a whole bunch of scientists to meet with adults and kids face-to-face and help them do hands-on science activities. Hashtag DIY SCI Zone, Z-O-N-E. Check that out. I'll post a link in the YouTube chat and the Slack chat. We're a little over halfway there, and we're all doing acts of whimsy where we hit various levels. And I will teach class in full Ghostbusters Holtzman costume.
Didn't you just do that now?
No, this is just the goggles. I have
okay.
like the jumpsuit and the gloves and everything. I will teach class as Jillian Holtzman. If we reach, I think, like the level just below 6,000, which is how much we need in total. So check it out. I'll post the link for that.
There better be pictures.
There will definitely be pictures.
That's in Seattle, right?
No, that's in Seattle.
Yeah, just around the corner.
Yeah, so sometime in the next couple weeks, I'll be teaching class if we can get all those donations.
Fantastic.
As Holtzman, yep.
Okay.
One more quick one. At the level, if we reach 45, when we reach, I think we'll reach it, 4,500, I will watch the movie Armageddon while live streaming my commentary, and you all will be invited.
I've been wanting to. Oh, that sounds great.
You want to do it with me?
I'm in.
All right.
I'm in.
We'll do it.
There.
Sounds like a good time.
Live.
Way to go, Adam Smith. You just broke Slack again. So clearly I need to. It's the @ on Slack.
We're doing it on purpose.
Well, that's fine. They're doing it to themselves. All right. Kimberly, where do people find out more?
People can find out more by following me on Twitter at AstroKimCartier. And I swear I am breaking my summer Twitter hiatus soon. And you can also check out my website, www.kimberlycartier.org.
Morgan.
Yep, you can follow me on Twitter at Morgan Renberg. I make no promises about breaking any Twitter hiatuses. You can also visit my website, morganrenberg.com.
Fantastic. Dave Dickinson, where do people find out more?
I'm a frequent contributor to Universe Today, Sky and Telescope, Listosaur, my own site, AstroGuys. I am a wannabe science fiction writer on Amazon under author David Dickinson. And I am documenting our travels across UK, Morocco, Spain, wherever we happen to wind blows us, across the internets, Instagram, Twitter. I'm AstroGuys with a Z, and I'm just everywhere.
Very cool. And we've got sort of an interesting project we're going to be talking about with you, yes. And we'll bring it up in a couple of weeks when we've sort of got things more solidified. But
right.
Okay, cool. And Dr. Frank Timmies, thanks again for joining us and talking about both supernova and astronomy education. And once again, for people who want to know how to study with you, where do they go? Oh, he's muted.
You're muted.
gfa.asu.com. Also go to edX. You can look for my Introduction to Solar Systems course. Just pop my name in under the edX platform. And then a shameless plug for everything I do is my website, CocoCube, CocoCubed.com.
Fantastic. Once again, I'm Fraser Cain, publisher of Universe Today. And if you haven't already, just subscribe. Just however you do, however one does, just subscribe to all the things on all the places, and then you know what? Actually, you specifically, you people, since you're watching this show live, you're super fans, you should click the little notification button, and then you'll find out when this show is actually happening. Your phone will freak out, and you'll get a chance to watch it live as opposed to being sad that you didn't get a chance to watch it live. So, yeah, put on that notification. Turn yourself from a regular fan into a super fan. All right, well, thanks everyone for joining us this week. Thanks for putting up with our technical issues. Thanks for our regular guest and our special guest. Thanks to Chad. Man, we're going to miss you. And we'll see you all next week. Oh, before you press the button, we're not going to do an astronomy cast today. We're going to do the astronomy cast on Monday. Pamela's caught in some kind of plane nightmare. So we're going to be doing the show on Monday. I'm going to talk to her about the space video games that I like to play, including Kerbal Space Program. So it should be fun. Anyway, that's what we're going to be doing on Monday. All right, thanks everyone. We'll see you all later.
Thanks. Bye.